Please title these notes Differential Equations Notes 2, Slope Fields, and write today's date. By the end of this lesson, you should be able to draw slope fields given a differential equation and also to match differential equations with their slope fields. So the idea behind slope fields is that in the past, when we've had a differential equation, we've had to do all the anti-differentiation and all the algebra to solve for y or f of x or whatever the function is. But the thing is that sometimes we just flat out can't do that. So another way that we can work with a differential equation is we can draw something called the slope field. And the slope field just means take a differential equation and use it to find the slope of the tangent line at a variety of points. Chart these points. Actually, I should say chart these slopes to produce an outline of the equation. So let's look at what this looks like, and then I think it'll make more sense. So draw the slope field of dy dx equals x plus 1 and sketch the particular solution that has initial condition f of 1 equals -1. So this here is a graph of f of x, but it's not really a graph of f of x. So what's going on is that, for example, at this point, let's say the point this is 1, 2, 3. dy dx equals x, which is 3, plus 1. So what I'm going to do is I'm going to draw a little slope, there's a little tiny slope, that has a slope of approximately 4. So let's see, so 1, 2, 3, 4 over 1, it would be something that would look approximately like that. And what I'm going to do is I'm going to keep doing that for all of these points on here. Now it makes it a little bit easier that I notice that this dy dx equals x plus 1 as long as x equals 3. So x equals 3 comma 1, 3 comma 2, 3 comma 3, 3 comma 0, up and down, these are all going to have the same slope of 4. So I'm going to sketch those in as best I can. And then if I come over here, it's x plus 1, it's going to be 2 plus 1, that's going to equal 3. So a similar slope up 1, 2, 3 over 1, so it's going to be something like that. So it's a little less steep, but not very much. And slopes that are like this, those can be a little bit tricky to sketch. That's okay. The main thing that are really important to sketch correctly are slopes of 1, -1, and 0. So for example, when x equals 0, 0 plus 1 is 1, so that should be a 45-degree angle. When x is -1, -1 plus 1 is 0, so that should be flat. When x is -2, -2 plus 1 is -1, so that should be 45 degrees pointing down. When x is -3, -3 plus 1 is -2, so it's going to be about at that angle. This line, 1 plus 1 is 2, so it's going to be again about at that angle. So notice that these ones, the sloping 2s, 3, and 4, are all kind of hard to tell apart. That's okay as long as these ones right here, the zeros and the ones and the negative ones, are accurate. So now the initial condition, that means this goes through the point 1, comma, -1. And all this initial condition means is it means that when we go to sketch the curve, the f of x, we're going to sort of follow these slope fields. The slope fields kind of tell us sort of like where to go. So for example here, the slope field, we're going this way. And we notice that once we get into closer to where x equals 0, then the slope tells us to flatten out a bit. And that when we hit this line where x equals -1, it's a 0 slope, so we flatten out. Then we hit this one and it goes up again. Then we hit this one and it goes up. And that here the slopes just keep getting steeper and steeper and steeper to do something like that. So here we've sketched our f of x based on the slope field that was given to us by f prime of x. Or actually, I guess this is y rather than f of x, because this was dy dx. But the general idea being, I guess this is really f prime of x, because I had f over here. At any rate, the slope given by this and the initial condition given up here. Okay, let's do another problem. Let's draw the slope field of dy dx equals x times y and sketch the particular solution that has initial condition 0, 1. So this is y, this is x. And what we can do is we can just go point by point and figure out what the slope is. So at 0, 0, 0 times 0 is 0, that's a flat slope. At 0 times 1, 0 times 0 is a flat slope. This is true for all the times when x equals 0. It's also true for all the times when y equals 0. So 1 times 0 is still 0, 0, 0, 0, 0, 0. At 1, 1, the slope is 1. At 1, 2, 1 times 2 is 2. 1 times 3 is 3. Let's see, 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6, so those should be getting steeper and steeper and steeper. 3 times 1 is 3. 3 times 2 is 6. These are getting steeper and steeper and steeper. They're a little hard to sketch, but the really important thing is that these slopes and this one be correct. 1 times -1 is -1. 2 times -1 is -2. 3 times -1 is -3. 1 times -2 is -2. -4, -6. -3, -6, -9. Okay, so -1 times 1 is -1. -1 times 2 is -2, -3. -2 times 1 is -2. -3, -6, -9, and so on. -1 times -1 is +1. -2 times -1 is +2. +3. -1 times -2 is +2. -2 times -2 is +4. +6. -1 times -3 is +3. +6, +9. So we've got something that looks like that. It's kind of a funky shape, but that's all there really is to drawing the slope fields. It does take a fairly long time if you've got both x and y. There really isn't a shortcut to it. If you just have one variable, like this original one did here, then all the ones with the same x value are going to be the same. If we just had y, all the ones with the same y value would be the same. If we have both x and y, we really do have to go each point by each point. So now the initial condition was 0, 1. So we're going to use that. We see the slope is 0, so it's going flat. Once it gets here, it kind of gets caught going up that way. And then here we see these slopes just get steeper and steeper and steeper till it heads off that way. Same thing here. This kind of catches it and pushes it up that way. And there we go, like that. Notice that if our initial condition had been down here, we would have had one going this way instead. If our initial condition had been 0, 0, it actually would have been a straight line. So the actual shape we get is very, very, very dependent on that initial condition. Let's do a third one as a check for understanding. Draw the slope field of dy dx equals y over 2, and sketch the particular solution to, actually that should be with the initial condition (1, -1). Okay, go ahead and draw yourself some little axes. Try this one on your own or restart the video when you're ready. Pause the video now. Okay, here's what I get for the slope field. Notice that every point that has the same y value is going to have the same slope because there's only y in the equation. So 0 divided by 2 is 0, 1 divided by 2 is 1/2, 2 divided by 2 is 1, and 3 divided by 2 is 1.5. Whereas over here, -1 divided by 2 is -1/2, -2 divided by 2 is -1, -3 divided by 2 -1.5. So with our initial condition at 1, -1 right here, if we follow that slope, it's sort of sending us in this direction, at which point this slope bends even more steeply down. And in this direction, it's sending us toward that 0 slope. So that means we should have this little asymptote right there. So our particular solution is going to look something like that. There is a twist that emerges when we have some problems, specifically ones that look like this. Okay, draw the slope field for dy over dx equals 1 over y and sketch the particular solution with the initial condition 1, 1. Notice that when y equals 0, this is undefined. So there's not going to be anything on this line right here. When y equals 1, 1 divided by 1 is 1. One divided by 2 is 1/2. One divided by 3 is 1/3. One divided by -1 is -1. 1 divided by -2 is -1/2. And 1 divided by -3, -1/3. So we can do our work with the initial condition just like we did before. There's the initial condition right here. But one of the things to notice is that even though we can draw this off like this relatively easily, it's just going to be heading off like that, if we go this way, there is no slope field here. That means we have to stop right here. Can't cross the x-axis because when y equals 0, there is no slope. Our next type of problem is to match slope fields and differential equations. And how we do that is the following. First, we're going to determine if the slope field changes based on x, y, or both. Pick at least one test point and determine from the equation what the slope should be. And then third, compare that slope to the one drawn. And determine if they match. So, let's have our slope fields. Okay, our slope fields are here, alpha, beta, gamma, and our equations are here. Take a second to go and write down the slope fields. And if you'd like to, you can go and try to get ahead of me. See if you can do these even before I explain how. Okay, now you've gotten those written down, let's take a look at them. So the first thing to notice here is that for alpha, the slopes are the same if the x values are the same. So the slopes do not depend on y. So that means we want an equation that depends only on x. So all these ones that have y in them can't be any of those. So our only options R1 or 2 dy dx is 1 over negative x. Okay, so let's look at it. Let's try some points. When x equals 1, we can see that the slope here is negative. So when x is 1, that has a positive slope. This is the one that matches. Because these slopes are negative, when x equals 1, just like they're supposed to be. For the second one, notice that the slopes depend on both x and y. So if I go right across the y's, there are different slopes. If I go right across the x's, there are different slopes. So that means our only options are these ones right here, 5 and 6. So now one of the things we notice is that at the point 0, 0, the slope is 0. So here at 0, 0, 0 over 0 is undefined. 0 minus 0 equals 0. So this is right. So this is our answer. And for the final one, the slopes depend only on y. So that means we're either going to have this one, dy dx equals 1 minus y squared, or dy dx is 1 minus y, or y minus 1. So let's go ahead and pick a point. Oops, it looks like this is not the right graph. So let's try a different graph. Let's see, the changes, the y equals 0 is the same. These should be slopes of 0, slopes that are negative, slopes that are even more negative. So I'm going to go ahead and replace this. If you're trying to solve this on your own, you couldn't do this one. There's a reason for that. Good work. Okay, so at y equals 1, slope is 0. So here at y equals 1, 1 minus 1 squared, that's 0. 1 minus 1 is also 0. Oops, so that looks like it's not a terribly useful test point. But this reason I chose this point here was to show you that sometimes that happens and sometimes you just need to pick a different point. So how about at y equals 2, slope is negative. Okay? At y equals 2, 1 minus 2 squared, that's 4. 1 minus 4 is negative 3. At y equals 2, 2 minus 1 is 1. That's positive. So this one should be negative. And there's our answer. This concludes these notes.